So we've went over several different quantization techniques. We talked about asymmetric and symmetric and the difference between those. We also talked about quantization per channel and also per group. And I've alluded to the fact that we don't have hardware to support integer arithmetic. And so our weights or any numbers that we're using, that we're storing in memory here in Colab or potentially on your own hardware, need to be in 16-bit or greater precision in order to be able to do any sort of operations with them. In Colab right now, using the free version, I don't have access to GPUs that support operations on lower bit precisions. I can't sit here and multiply negative 47 that's an 8-bit precision with 127 that's an 8-bit precision. It'll create an overflow error and we'll get an incorrect answer. So we have to cast these back up or dequantize them to get them back to the original values. At the very least, we need to cast them back up to 16-bit. So before we do any sort of inference in a neural network, if we're using hardware that doesn't support lower bit arithmetic or integer arithmetic, we do have to first dequantize our weights and then cast them back up to a higher data type and then do multiplication using them there. All right, so I'm going to copy and paste in an example weight matrix. This is going to be our example weight matrix that we're going to use in our to simulate what it's like to do inference. We're going to use this weight matrix as our neural network, which is just a single weight matrix with no bias, and we're going to multiply it against our original tensor right here. And so what we first need to do is we need to quantize this input weight matrix here. I'm going to create a function called Quantized Inference, which is just going to take as input these weights that are already pre-quantized, and then it's going to do the multiplication for us with our input tensor and our input weights that are already quantized. So we're going to take as input our input tensor, which will be our original tensor that we've been using, and then we're going to take as input our quantized weights, which is going to be this input weight matrix here, quantized down to lower bit precision. And as well, we'll need our scale, 0 point, and group size because I want to do per group quantization here. So what we're going to do first is we're going to dequantize the quantized weights. And then, so dequantized weights is going to call I'm going to modify this a little bit. I'm going to call the per group dequantize. And that's going to take as input the quantized weights, the scale, which in this case is a scale per channel, a group size, and a group size. There you go. And then I am going to do, I'm not going to do that, I'm going to perform the matrix multiplication between the dequantized weights. I'm going to make sure that the dequantized weights are equal to whatever d type the input tensor is. And then I'm going to change this up because the actual formula for a neural network is the weight transpose times x, which the weights here is the dequantized weights. I'm going to transpose them, and then I'm going to do a matrix multiplication between them transposed and the input tensor. And then I'm going to return the output tensor here. And now in this next cell, what I'm going to do is I'm going to quantize the input weights. And it's going to be per group, we'll call per group quantize. I'm going to take the Gemini completion. And so we're passing in the input weights. Our target D type is int 8. And then our group size is 2. That's exactly what we're looking for. And then let's see what it looks like. Okay, so this is our input weights quantized to right here. And we have again, we have 6 scale parameters. And then next, let's just run inference with this quantized weights here. I'm going to pass in our original tensor as like our input data, our input tensor. Our quantized weights are going to be obviously the input weights here, example weights quantized. And then I'm going to pass in our scale. And then I'm going to pass in the scale, 0 point, and group size. So the scale is going to be equal to this scale right here. The 0 point will be 0, and then the group size is going to be equal to 2. And then let's see what we get as an output. So this is our output. This is the result of multiplying the dequantized weights here with the input tensor. Now, these are some really big numbers. How do we know that this actually is is accurate? Well, as a baseline, what we can do is we can compare this to what the output would be like if we had just kept the input weights the same way, right? We hadn't changed them at all. And let's do that. So we're going to transpose those weights that are in 32-bit precision, and we're going to do a matrix multiplication with the regular tensor. And then as you can see, this is what we get. If you look at these numbers in the top row especially, they don't look much different. You know, they look roughly the same. Obviously, keeping the weights the same and doing the matrix multiplication with just the input weights, non-quantized, gives you, it's slightly different, but it looks to be like pretty accurate. You know, there is some information loss. We know that with quantization. But let's go ahead and see like exactly what the error is. I'm going to use our compute quantization error to calculate the difference between this tensor and this tensor. And remember, our compute quantization error, all it does is calculate the mean squared error between two different tensors. So it's actually a good measure of difference between these two tensors. And what we get is we get a really large number. I only think that because we actually have some really big numbers in here, so it's kind of skewing it a little bit. But if you just look at, I'm going to return the difference tensor here, and I'm going to run this again. If we just look at the difference tensor, which takes the difference, the absolute difference between each value, it's really not that much. You know, being off by 623 on a, on a number that's as big as 82,482, it's not, to me, it's not that big of a deal. And now these errors do add up over many layers in a neural network, so that may matter on a grander scale. Again, apply it to your use case, see what works for your application. But here, you can see that this is kind of accurate, right? It's pretty accurate.